All right, so continuing from our thermal physics, right? We have to go ahead and we have to talk about solids, liquids, and gases. And we have to obviously talk about the kinetic theory of matter and the Brownian motion. That was something that we were left with. So when we take a look at solids, liquids, and gases, so solids, as you know, what do we know about solids? We know that solids have a fixed shape and fixed volume. Its particles are held in their regular arrangement. In their fixed places by strong forces of attraction. Now, when we are going to talk about it, so the molecules, the particles can only vibrate in their fixed position. Then we have our liquids. Liquids have a fixed volume but a variable shape. And the particles are close together to each other, but not as close as they are in solids. And they have forces of attraction between them. They are free to move, but within the confines of the liquid. And then, of course, we have our gases. Gases have no fixed volume and no fixed shape. The particles are spaced out. The particles are spaced out and have very weak forces of attractions. And they are free to move. And they can move at high speed. And they can collide with each other. And they can collide with the walls of the container, which exerts pressure. Now, when we talk about our motion of your gas particles, okay, so the motion of gas particles is referred to as your Brownian motion. It's named after a scientist who discovered the movement of the gas particles or small particles basically, and his name was Robert Brown. And he basically noticed something really interesting. He noticed that he had a petri dish which had some pollen grains in it. So he noticed that the pollen grains seemed to be moving about, even though there were pollen grains in the water. Okay, so the petri dish had water in it and there were pollen grains in it. So he noticed that the pollen grains seemed to be moving about. So he wondered, why are the pollen grains moving? There's nothing there. You just have water and you have the pollen grain. There is no wind, no air. Why is the pollen grain moving about? So he decided to perform an experiment. And the experiment that he performed was that he took like a chamber, and that chamber had a lot of smoke inside it. Okay, and inside this chamber there was a lot of smoke. And in this, he placed a microscope, and along with the microscope, so he placed a microscope and he also placed a light source. Right, so from over here, shown the light. So the light source, why did he place the light source? Because the light source illuminated the particles of the smoke, the particles of the dust. And with the microscope, he observed the particles. So what did he actually observe? He actually observed that the particles that the particles had very random and haphazard motion. So they had a very haphazard and a very haphazard and random movement, right? So they were moving around randomly. There was no pattern to it. There was no, logic behind it. They just had a very random sort of movement. Haphazardly, they were moving around in the setup. So this is basically Brownian motion. Now, when we talk about the kinetic theory of matter, so in the kinetic theory of matter, what it basically states is this. So, according to kinetic theory of matter, right? So, as the temperature rises or as the heat energy increases, the molecules vibrate faster. I'm saying molecules, it can be particles, ions, whatever the gas is made up of. The molecules will gain kinetic energy. And they'll move faster. Right? And as they move faster, there will be more collisions between them. Now, we can use this concept of kinetic theory of matter to explain a lot of things. You can use it to explain, for example, the change in state. They gain, for example, more kinetic energy. Okay, so they move faster. And as they move faster, they will move further and further away from each other. Now, when we talk about our kinetic theory of matter, we can use this concept to explain anything. We can use it to explain the change of state. We can use it to explain why the temperature rises. We can also use it to explain a really important concept, and that is the concept of that is the concept of your evaporation. Okay, so when we talk about our evaporation, okay, what exactly is evaporation? Because you'll find a lot of questions related to it, and you might wonder what is the difference between evaporation and boiling point, because evaporation and boiling are both changes from liquid to gas. Okay, both of them are changes from liquid to gas. So what is the difference between evaporation and what is the difference between your boiling? So when we talk about evaporation, okay, evaporation is when liquid turns into gas. When liquid turns into gas, that is basically your evaporation. Now, when we talk about evaporation, what basically happens in evaporation? More energetic molecules will escape the surface of the liquid. More energetic molecules, because when you talk about any liquid, okay, so all the molecules do not have a fixed amount of energy. They always have a variable energy. Some molecules will have less energy, some molecules will have really high energy. So evaporation is the escape of more energetic molecules. Those molecules that have high energy, they will escape the surface of the liquid, and the less energetic molecules will be left behind. Right? And remember this, evaporation always has a cooling effect. That is how your sweating works. Your sweating cools you down, right? This is how it cools you down because of evaporation. The sweat evaporates from your body, and that causes your body to basically cool down. The reason for that is because the more energetic molecules have escaped the surface of the liquid. So the molecules that are left inside the liquid are less energetic. Since they have less heat energy, they obviously also have less kinetic energy. And since they have less kinetic energy, so what is going to happen? The temperature is going to be less, because temperature is a measure of kinetic energy. So the temperature is actually going to be lower after evaporation has happened. Okay, after evaporation has happened, after the water vapors or after the vapor, more energetic molecules has escaped, the less energetic molecules will stay behind. And as they're going to stay behind, that is going to basically cause the molecules will have less kinetic energy. So the temperature is also going to be lower. Now, when you talk about evaporation, evaporation occurs over a range of temperature. This is where evaporation is different than boiling point. Boiling point is a specific temperature. So for water, the boiling point of water is 100 degrees centigrade. At 100 degrees centigrade, we are going to see boiling. That's it. Evaporation can occur over a range of temperatures. It can happen at 50 degrees, 60 degrees, 70 degrees. Put it outside in the sun, you'll see evaporation. So evaporation is over a range of temperatures, and it is simply the more energetic molecules escaping the surface of the liquid. In boiling, in boiling, there is a specific temperature at which it is going to boil, right? So that is the major difference between evaporation and boiling point. Now, evaporation depends upon temperature. If you increase the temperature, obviously the evaporation will increase. If you increase the surface area, the evaporation will increase. If you decrease the humidity, the evaporation will increase. Why? The reason is because that there will be less water vapor. Okay. If there is less water vapor, then the concentration gradient is high, because there is high concentration gradient inside. For example, we have placed a jug of water outside. So in this particular case, because the inside the air, the water vapor is less, and inside the jug, the water vapor is higher concentration. So the water vapor moves from higher concentration to lower concentration. So the water will evaporate quickly. If it's really humid, then the concentration of water vapor is high. So that will affect the diffusion and it will affect the evaporation. Then obviously we have wind. Higher the wind, higher the rate of evaporation, and the logic matches the same logic as humidity. If the wind is high, it will quickly blow away all the water vapor. So the concentration difference is going to be high, right? Because all the water vapor is constantly being removed. And as a result, the molecules will move out faster. Right? Making sense so far? Haja, I hope no confusion regarding anything.
No.
Okay. Now, when we talk about temperature, so I went over all your thermometers with you. Now, let me go over with you the scales that we use for measuring temperature. When you talk about the scales that we use for measuring temperature, so there are three major scales that are being used. There are many, actually, there are more scales as well, but there are three that we use commonly. We have the we have the Celsius scale. We have the Fahrenheit scale. And then you have the Kelvin scale. Right? So when you talk about the Celsius scale, okay, so when you talk about the Celsius scale and the Kelvin scale, these are the ones that are used quite commonly. When we talk about the Celsius scale, okay, so one is the Celsius scale. When we talk about the Celsius scale, that's obviously the one that we use really commonly. But the Celsius scale is when we talk about the melting of ice is 0 degrees centigrade and the boiling of water is 100 degree centigrade. Now, when we talk about our scale, okay, I'm going to draw for you the graph for okay. I'm drawing for you the graph of, let's say, energy. Okay, on the x-axis, I'm doing energy, kinetic energy. And on the y-axis, we're doing temperature, but this is in degree centigrade. So over here, the graph is going to come out looking something like this. Right? Notice that notice over here that when the temperature is 0 degrees centigrade, okay, when the temperature is 0 degrees centigrade, the energy is not equal to 0 degrees centigrade. If you look on the y-axis, the energy has some value, right? The energy is not equal to 0. This is the problem with the Celsius scale. If you remember, you and I had discussed that the temperature is measure of average kinetic energy of the molecules. So temperature is supposed to tell you how much kinetic energy the molecules have. But at 0 degrees centigrade, the molecules still have a lot of kinetic energy left over. Okay, so that is the problem with the Celsius scale. It's a linear scale, but it does not give you a direct measure of the kinetic energy of the molecules. A better scale and the best scale that you can use for your measurements is the Kelvin scale. Similar graph I'm going to show for Kelvin. Energy is in joules and temperature is in kelvins. Your graph is going to come out looking like this. A directly proportional relationship. When the temperature is 0 Kelvin, the energy is also 0. In fact, energy is almost close to 0. If you actually, at this point, look at the properties of whatever gas, right? Whatever gas you're studying. If you actually look at the properties of that gas, you will see that the energy of the molecules is as close to 0 as possible. The molecules are very much stationary. They are barely moving. The energy is literally as close to zero as possible. This is known as absolute zero. Absolute zero is 0 Kelvin. So the Kelvin scale is the one that has that has absolute zero. In the centigrade scale, the zero means even though the temperature is zero, but molecules will still have kinetic energy. In Kelvin scale, if the temperature is zero, molecules have no kinetic energy. So absolute zero is equals to 0 Kelvin. And at this point, molecules have almost no kinetic energy, no measurable kinetic energy. We can't measure at the very least. See, so that is what we can see. And if I take this graph of mine, the one I drew for the centigrade one, okay, and I extrapolate it means extend. If I extend it backwards to this point, okay, at this point, now the energy is zero. So when the energy is zero, your temperature is going to be minus 273 degrees centigrade. Okay. So, so Kelvin scale is basically considered to be the best scale because it gives you a direct measurement. If the temperature is zero, the energy is also zero, right? It gives you a direct measurement. Centigrade scale is also a good scale, but it does not have an absolute zero. The zero of centigrade does not mean that the energy is going to be zero as well, right? And if we extend the graph backwards until we get to zero energy, so the temperature at that point is going to be minus 273 degrees centigrade. So 0 Kelvin or minus 273 degrees centigrade, this is our absolute zero basically. Okay, this is the point where we said the molecules are now at absolute zero. And so 0 Kelvin is equals to minus 273 degrees centigrade. And if you want to convert your Kelvin, or if you want to convert Celsius into Kelvin, all you have to do is do plus 273. Okay, whatever the temperature is in Celsius, 40 degrees Celsius. So you just do plus 273 and you will be able to find the temperature in kelvins. So this is what we need to know about your temperature scale. Mhm. Okay, I hope everything is making sense so far, Hajar, right? No confusion?
Um, can you just explain the part
Yeah,
of
go on.
absolute zero?
Yeah. Absolute zero is the point at which the molecules will have no kinetic energy or almost, I mean, the kinetic energy is so low at that point that at least you and I cannot measure it anymore. Okay. So 0 Kelvin, absolute zero is that temperature, that particular temperature at which the kinetic energy of the molecules is zero. The molecules are not moving, they will be stationary, they will be staying exactly as they are. So that point is referred to as absolute zero. Absolute meaning that, that this is it. This is the absolute point. Like we cannot go any lower than this. We cannot go any lower than this. This is the minimum zero that we can get to, right? So absolute zero. We had studied, if you remember, I had told you that temperature is the measure of average kinetic energy, right? Temperature is the measure of average kinetic energy of the molecules. Now, in the Kelvin scale, the temperature directly corresponds to the energy, right? Meaning that if the temperature is 0 Kelvin, that actually means what? That the energy is zero. So this is the absolute zero. In the Celsius scale, if the temperature is zero, the molecules still have energy, right? Even if the temperature is 0 degrees centigrade, the molecules still have some energy, right? So in the Celsius scale, the 0 of Celsius scale is not the absolute zero. 0 degree Celsius is not the absolute zero because molecules still have kinetic energy at that temperature. But 0 Kelvin is absolute zero. Okay. Meaning that at 0 Kelvin, they have no kinetic energy whatsoever. Hence, absolute, like the minimum. That's it. We can't go lower than this. This is the minimum zero that we can get. At this point, molecules are done. They have no more kinetic energy left, right? If they have no kinetic energy, then they have no temperature because temperature is a measure of kinetic energy. So 0 Kelvin is equals to minus 273 degrees centigrade. Okay. So if the temperature happens to be 0 Kelvin, or if you want to measure in Celsius scale, then it will be minus 273 degrees centigrade. So at 0 Kelvin or at minus 273 degrees centigrade, the temperature, the energy of the molecules is going to be zero. That's it. The molecules cannot cool down anymore. They are at the minimum energy that they can be. They can't cool down anymore. The temperature cannot decrease anymore. Excuse me. That is referred to as absolute zero. Okay. So absolute zero in the Kelvin scale, it is 0 Kelvin. In the Celsius scale, when we reach the temperature of minus 273. So in Celsius scale, minus 273 is the absolute zero. Like we can't go below minus 273. That's it. You can't take the temperature below minus 273. That's the lowest we can go. Or if you're measuring it using the Kelvin scale, so it's 0 Kelvin. You can't go below 0 Kelvin. Right, Hajra? I hope it's a bit more clearer now.
Yeah.
All right. Now we have to go ahead and take a look at some property of gases, especially related to the pressure of the gases. There are two laws that are a part of your syllabus: Charles' law and Boyle's law. All right, the first thing that we have to understand whenever we talk about pressure in gases is what exactly is pressure. Okay, now if I've not gone over general physics with you yet, but when we talk about pressure, so pressure is basically, if you remember, force per unit area. Now, how do gases exert pressure? In gases, basically, okay, first, before we go over this, let's go over a few gas laws. Okay, there are two gas laws that are part of your syllabus. One is the Charles law, and the other one is the Boyle's law. So when we talk about, first let's take a look at Charles' law. I will use the laws and I'll explain to you how does the gas exert pressure. So Charles' law basically states that pressure and temperature are directly proportional to each other, provided that volume of the gas remains constant. So, what this basically means is that pressure and temperature are directly proportional to each other. So, if temperature increases, the pressure also increases. That's what it means. Okay. If pressure increases, the temperature also increases. So, when we talk about our pressure, okay, how does this happen? As temperature increases, what happens? That the molecules move faster. Molecules gain kinetic energy. And they will move faster. As they will move faster, there will be more collisions with the wall of the container. As there will be more collisions with the wall of the container, the as there will be more collisions with the wall of the container, what is going to happen? The molecules will exert force. And force per unit area is equals to pressure. So pressure also increases. So this is basically what Charles' law actually states. And for this one, you can go ahead and you can use a formula which is P1 is equals to T1 divided by P2 divided by T2. Okay, so P1 is pressure 1 divided by pressure 2 is equals to temperature 1 divided by temperature 2. No other balloon. No working. Yeah. Now, along with Charles' law, we have another law that is Boyle's law. Boyle's law states that volume and pressure are inversely proportional to each other. Provided the temperature remains constant. This is mommy. So what does this mean? This basically means this. Let's say the volume of the gas decreases. Okay, volume decreases. If the volume is decreasing, that means the gas is being compressed. So as the volume will decrease, the gas is going to be compressed. Okay. Now what is going to happen? The molecules will come closer together. Since they are now closer together, there will be more collisions with the wall of the container. So that means there will be more force exerted. What that means is that pressure is force per unit area. So pressure increases. So if you decrease the volume, the pressure is increasing. If you will increase the volume, the pressure will decrease. So pressure is inversely proportional to volume. Okay, pressure is inversely proportional to volume. And when we talk about the graph, okay, so the graph is going to look something like this. On the x-axis, I am putting pressure. And on the y-axis, I'm putting the volume. Beautiful. So it's an inversely proportional relationship. It means that your graph is going to look something like this. Okay? Or I can make a graph like this. On the x-axis, I can put pressure. On the y-axis, I can put pressure in Pascal. And on the x-axis, instead of putting volume, I can put 1 upon volume. If I put 1 upon volume, then I will see a straight line. Why? Because pressure is equals to 1 upon volume. Okay. So pressure is equals to 1 upon volume. So if I put volume, I will get a curve. If I put 1 upon volume, then I get a straight line. So you can see that pressure is inversely proportional to volume. So if volume is high, pressure will be low. And if volume is low, pressure will be high. And the equation for this is P1 V1 is equals to P2 V2. Right? P1 V1 is equals to P2 V2. So this is basically what your gas laws are about. So you should know about what these gas laws are, and you should also be able to use these formulas to do the calculations, right? Making sense, Hajra? Any confusion in anything or any part that's not clear?
No.
Okay, good. Okay, I just want to add a concept over here for you. Okay, so over here, when I told you that I want to add something actually, more collisions with the wall. Okay, so more collisions with the ball actually mean that there is going to be greater rate of change of momentum. If you remember, or you've not done it with me, so if you don't remember, it's okay. But basically, force is equals to change in momentum per unit time. Okay, so force is equals to, this is rate of change of momentum, right? Divided by time, it becomes rate. So since there are more collisions with the wall, there will be greater rate of change of momentum. So that will leads to greater force being exerted. Right? Greater force per unit area. So that's why the pressure increases. Okay, so just wanted to add that particular line that more collisions mean greater rate of change of momentum. So there is greater force per unit area. Okay. All right, that's it, Haja. Okay, that's where we're going to stop over here for today. Now we're just left with conduction, convection, radiation. That's it. Otherwise, we are done with the topic of thermal physics. We're only left with conduction, convection, and radiation portion. That's it. So we're going to go ahead and stop over here for today. Haja, if you want to go ahead and pray before chemistry, you can go ahead and do that.
Okay.